Today we're going to start the first of 2 weeks on electrical current and physical electricity. This is something that you do every day, and I wanted to spend a little extra time because I think the understanding that you'll get from these 2 lectures will serve you well, even if you do not pursue a scientific sort of degree or an engineering kind of degree. It will help you understand how things around your house work as well as other things. So first of all, it's important to understand that there are 2 types of current. Current electricity is electrical charges in motion. We had a whole week where we discussed static electricity, and I emphasized then that the electricity was not moving, or the electrons were not moving. Now we're talking about electrons and positive charges that are moving. And so current electricity is that electricity that moves through a circuit. And a circuit is a term for any complete pathway in which the electrons can move. Now what you see on the left here is what's called direct current. Direct current is current that can flow in only one direction. As you can see here, the current is flowing in the counterclockwise direction. That is, on the bottom from left to right, on the top from right to left. It starts at the negative pole of your direct current source, which is commonly a battery, travels around, passes through the load, and a load is anything that is operated by electrical energy. It can be a light bulb, it can be a toaster, it can be anything whatsoever, a train, your cell phone, etc. Once the electricity does its job in the device, it then leaves the device and travels back to the source, completing the circuit, and travels into the positive pole of the battery. So this is a direct current. It only travels in one direction. Alternating current, on the other hand, alternates from one direction to the other. At one time it'll be going clockwise, another time counterclockwise. Alternating current, shown on the right here, is the most common type of current found in homes in the United States. As I said, the most common time that we would run into direct current in the United States is with battery-operated materials. In Europe and foreign countries, however, there are many other areas that are operated by direct current. Homes can be wired up by direct current, which is why when you go to Europe, you frequently need an adapter to operate your devices. Now, electrons move from one place to another because of the attraction or repulsion between the charges. As I said, you start at the negative end, which is on the right here. The electrons then flow through the light bulb, come around to the positive end. They are attracted by the positive end of the battery and repelled by the negative end of the battery. And so that's how they are driven. Now you'll notice that the direction of the current is actually in the opposite direction of the flow of the electrons. Now some people find this confusing, but the reason that this happens is because, or the reason that it is shown this way is because that when they first began to study electrical currents, they decided by convention to say that the flow of current is the direction that positive charges would move. And so since the negative charges are moving counterclockwise, the positive charges are moving clockwise, and that is by convention the direction of current. So a wire that carries current by itself doesn't necessarily have a charge. In other words, if we didn't have this hooked up so that it would complete the circuit, then the wire itself would not, and frequently does not, have an electrical charge. Now that does not mean it doesn't have electrons. It just means that it does not, in a static situation, generate a charge. Now you can many times consider electrical flow much like the flow of water through a pipe, where the water represents the flow of electrically charged material, and the pipe represents the wire which is carrying the charge. In that respect, the pipe tends to flow, and this is on the bottom here, from high pressure to low pressure. You have a higher pressure on the left and a low pressure on the right, so the water flows out in that direction. And that difference in pressure is what provides the energy or force for the flow of water to move through the pipe. Similarly, a difference in charges from the left to the right, in that the higher negative charge is on the left and the lower negative charge is on the right, such that you have a flow of electrons from left to right, and that difference in flow is what causes or drives the electrical movement, and that is called voltage. And that electrical difference, which is also called electrical potential, is measured by what we call, the unit is called a volt. Now the flow itself, how much water passes through the pipe in a certain period of time, similarly how many electrons pass through the wire in a certain period of time, is the current. It's what's called the current. So the current is the flow of electrons per unit time, and it's measured with a unit called an ampere. And so the rate at which the charge flows through the wire is what is important, not the total amount of charge that passes through. The third unit that you need to understand is power. We've already talked about power in terms of mechanical energy. Power in terms of mechanical energy is the work done per unit of time. You take work and divide that per unit of time, so it's joules over seconds. In electrical terms, power is the voltage times the amperage. And if you multiply those two together, you get a similar unit of power. It's called a watt. So volts times amps equals watts. Now, your home, when you're billed for your electricity, you're billed in terms of kilowatt hours. Now, a kilowatt is just 1,000 watts. But what does this idea of hours being added to that, what does that mean? Well, just to look at, a single kilowatt hour could microwave 13 meals. It could power a CFL light for 56 hours. It could power a space heater for 40 minutes. It could power an incandescent light bulb for 17 hours. It could operate a refrigerator for 5 hours. Or it could charge your cell phone for 278 times. All of these various things can be done with 1 kilowatt hour. But what does this mean? Well, the amount of electrical energy used by any device is dependent on two factors: the power and the time in which it operates. And so the unit for electrical energy is kilowatt hours. So let's take a look at a couple of problems with the principles that we have just talked about. So a microwave oven is plugged into an outlet that provides a voltage difference of 240 volts. So your voltage that's driving the flow of electrons is 240 volts. Now the current, the flow of electrons, is 12 amps. So how much power does this oven use with this flow of 12 amps? So in order to do this problem, you would have to remember that power equals volts times amps. So in this case, it's going to be 240 times 12. And so let's see, that's 480 plus 2400. So that's going to be 2880 watts. So the power usage by this per second is 2880 watts. Now if you run the oven for 12 minutes and power costs 6 cents per kilowatt hour, how much does it cost? So First of all, you have to take the 2880 watts times 12 minutes. But remember, it's 60 seconds per minute. That's going to equal 2.07 times 10 to the 6th watts seconds. Okay, so 2.07 times 10 to the 6th watt seconds times, there are 1,000 watts in a kilowatt, and there are 3,600 seconds in an hour. That's 60 seconds per minute times 60 minutes in an hour. So if we take this number and divide it by 1,000, and then divide it again by 3,600, we get 0.576 kilowatt hours. And it says that a kilowatt hour costs 6 cents, so if we multiply that by 6 cents per kilowatt hour, operating this microwave for 12 minutes costs about 3.06 cents. 3.6 cents. 3.6 cents. The second problem looks at 4.5 watts of power used with a current of 0.6 amps. So what is the voltage difference that's powering this flashbulb? Well, we know that power is equal to volts times amps. So volts is going to equal to the power divided by the amperage. So that's going to be 4.5 divided by 0.6. So that's going to be 7.5 volts. Now let's talk about conductors and insulators and the concept of resistance. Remember that insulators are things that do not conduct electricity. Wood, like a toothpick, a piece of rubber, like a rubber band, a Q-tip, things of this nature. A pencil is marked here as something that sort of intermediately conducts electricity, and then there are things that do conduct electricity, like a penny, which is made of copper, aluminum, a nail, which is made of iron. Now, when you think about the resistance to flow of electricity, think about it in terms of the fluid again. If you have a crimp in your pipe, then the flow of fluid through that crimp slows down. And so it will impact the flow of material. If you release the crimp, then there's less resistance and the flow will increase. Similarly, if you have a wire that has more resistance to it, it causes an impedance of flow of electrons. Whereas if you have a good conductor, like copper, you have less resistance. And you may have heard of the concept of a superconductor. And a superconductor is a material that has virtually no resistance to flow. And that would be something very valuable if we could develop one that didn't require super cold temperatures. So a conductor is a material through which electrons can freely flow. An insulator is a material in which electrons cannot necessarily flow. And resistance is the amount that a material hinders or resists the flow of electrons. So here's a third unit. So we have the volt, which is the potential difference that drives the movement of electrons. We have the amp, which is the flow of electrons or the amount of electrons per unit of time that moves through a material. And then the third unit is an ohm, which measures how much a material resists the flow of electrons.